Good morning, everyone. Welcome to the first lecture in 21. First, happy year. And we start as usual with the privacy policy. Well, it's enough privacy policy. We have heute guests from the Carolo Cup team, Team Galaxis, who, it's a student team participating in Carolo Cup student competition, and they would like to introduce themselves. So I will stop my screen sharing. And who is going to present Carolo Cup today?
Das ist David.
Okay, David.
Ich weiß nicht, aber ich glaube, er ist drinne. Ja. Okay.
Yeah. Can you see my screen?
Yeah.
Okay, perfect. Then maybe let's just start. So my name is David. I'm one of the two team leaders of Team Galaxis. Our team, as Bassam already pointed out, competes in the Carolo Cup. This is a competition where a small 1 to 10 scale model car has to drive around a track autonomously, right? You can see this just playing in the background, right? This is just to give you an idea. The car is supposed to drive around this track in the shortest possible time, making the fewest possible errors. And we are looking for new team members. So if you're interested in self-driving, as you probably are if you're listening to this lecture, and you have maybe a special experience in one of these areas, right? So computer vision, control engineering, AI decision-making, or if you have experience in mechanical engineering, those are smaller tasks, but we also would like to have more experience in those areas. So if you have experience in mechanical engineering or electrical engineering, or if you have another skill that might be helpful, then we are very happy to get into contact with you and to talk to you. You can approach us either via email, just write us an email, or you can talk to us directly on our Discord server, which we are on Tuesdays, Friday afternoons, and we will also be on the Discord server after this lecture from 12 to 13 o'clock. So you can find the link to our Discord server on our website, as well as our email address. So if you're at all interested or think this is interesting and want to contribute, then feel free to contact us and have a fun and interesting lecture. Thank you very much. I'm just going to stop my screen share.
You are muted, Bassam.
Thank you, Patrick. So today is going to be a fun lecture. Today, we are going to play some games, but before the games, we have to go through some slides. Yeah, today we are starting with a new topic, network and distribution. And yeah, as in every part, we look firstly at the course contents. And we have already arrived the third topic, network and distribution. The remaining parts, machine perception, software architectures, and testing concepts, and case study are going to take around 3 lectures. This part is going to take 3 lectures. So we are almost in the middle of this course. So in every part, we take a look at the lab architecture to point out where we are in the lab architecture to be able to map the topics later to the lab. So we are in the coordination and decision-making modules. So after these 3 lectures, you will be able to coordinate single agents in the lab. They are model-scale vehicles. And we'll take a look at the literature. Yeah, this book is already listed in the module description, Control Theory of Digitally Networked Dynamic Systems. This further literature is new, isn't listed in the module description. Yeah, but it is available in the library, I think. The name is Network Control of Multi-Agent Systems. And of course, we look also at own literature. So for the flipped classrooms, we will have 2 of them. You have to take a look at my PhD thesis. And we look again at this slide. We discussed this slide in details in the introduction. So the definition of networked systems and the contribution of networked systems to perception and decision making. But I repeat it a little bit here. So network systems are also called connected, especially in the area of vehicles. We speak rather of connected vehicles than networked vehicles, but I call them networked vehicles because we speak more about network systems and the focus is more on the systems. So they are just definitions. And for the connection or for the network, we need communications, and communications bring, of course, some drawbacks with them, which we will see during this lecture. Some of them we will handle here, some of them not. Important drawbacks are, of course, the overhead coming with the communications, the delays coming with the communications, and the data losses. Not every single data packet arrives technically at the target, and this is, of course, a drawback. So network systems consist of interacting systems, and in the introduction we have discussed a lot about the word interacting and the meaning of interaction. So please refer to the introduction. And what we expect And this is why we do it here, is contribution to better perception and decision making. So I give two examples in the introduction about the contribution to better perception and decision making, and repeat the slide in a minute. So the challenges arising from computation time and communications are feasibility and quality, and we will speak in detail in this part of the course about the feasibility and also about the quality, but our focus will be on the feasibility. So I'm seeing something in the chat. Will the last lecture be held? So the last lecture at all in this term is going to be on February 11th. So the contribution to better perception and decision making, we have here on the left this example where we have a vehicle driving to the north, two vehicles driving, or a vehicle driving to the south, and number two is standing. A pedestrian is going to cross the road. Vehicle one isn't able, or the driver of vehicle one isn't able to, or the perception system, because we are speaking about autonomous vehicles, isn't able to see the pedestrian. So vehicle three is, of course, able to recognize the pedestrian, and it communicates its data to vehicle one. Vehicle one can consider the pedestrian. This is a typical example in perception, and a typical example in decision making is the intersection, where vehicles are heading to the intersection. They have to cross in different directions, and they have to coordinate to cross the intersection as efficient as possible and also as fast as possible. Okay. Now we look at a known example for you, the pedestrian walking, but this time as network MPC. So the task, you know already, follow the line, act as little as possible, consider physical and logical limits. The plan, use discrete model to anticipate your free movement for 2 steps. This time, for simplicity, we want just to have a prediction of 2 steps. Consider your physical body limits. Consider physical and logical limits of your action, position, orientation. These are from the pedestrian walking, and now we have the pedestrians walking. So as network MPC, so the task here is don't collide with each other. So this is important here. And yeah, the planning part is plan your action for 1 step. For simplicity, we are taking here just one step. And what you are going to do is to plan, communicate plan, this is new, and to act. So in MPC, we had plan, act, and here we have communicate, plan. Well, I need two of you to play this simple game. So if you would like to play, just raise your hand and we can start the game. I need 2 players, so you have to be fast to be able to play. So this lecture consists of games. You have to play. There is no way of letting me play. I cannot play for you.
Okay, I would join the game.
Okay. Paul is the first, so we need a second player. Don't worry, I will help you. It is it is simple. There is in this game there is nothing complicated to do.
Well, I will join. I have no idea what I'm supposed to do, but I will join.
Okay,
Me neither.
We have Julia, right?
Yeah, exactly.
Okay, Paul and Julia. Okay, I need you now to write me a private chat. So just each of you should just write me just a dot in the private chat that I see you. So Paul private.
I think that should be private now, right? So only.
So now I have Paul. So Paul, do you see the dot?
Yes.
Okay. So you're the player number 1, and this is your message. You don't have to do anything, just take the message. And this is Julia. You see the dot, right?
Yep.
And now you see the message. Right?
Yep.
Okay, now each of you has its message. So player number 1 is Paul, player number 2 is Julia. So the game here, player number 1 is heading to the east, player number 2 is heading to the west. And as we saw in the last slide, predict 2 steps and communicate and then act. So first you have to plan 2 steps. And here for simplicity, I have defined the steps so that steps are equidistant. So 0, 1, 2, 3. And you are allowed just to change your position 1 step to the right or 1 step to the left. And for simplicity, it is also perpendicular to the straight line. So now you have, each of you has to tell me where do you want to be in the next step. So
I have one question. Can we just move on the middle line, or can we also go
Yeah,
up and down?
yeah. You have 3 choices: straight, left, and right. So you have to just write to me straight, left, right. So 2 steps, and yeah, and the plan is 1. So the prediction horizon is 2 steps, and the plan where you are allowed to plan the action is one step. Of course, the action is always 1 step.
So we're supposed to write it as a message, right?
Yes.
Yeah. Okay.
So I see Paul saying go to the right, and Julia saying also go to the right, each from his or her perspective. So I'll.
Oh, wait a second. Oh, I'm sorry. I think I confused the players. Well, which player was I actually?
2.
Oh, yeah. Okay. So I was okay. Sorry. Wait. Oops. Yeah.
Well, so we have here player 1 is allowed to predict 2 steps, and we have player 2 is allowed to predict 2 steps. So player 1 will see this point and this point, and player 2 will see. Okay. So the players will see these points. Why did you decide to change?
Player 2.
2, yes.
Because I think that's the direction I want to go to, and there's nothing in the way, so I can just go further. For the next 2 steps, there was nothing on my way.
Yeah, but you decided to. Okay. Maybe there is something confusing. You are allowed to avoid to the left or to the right, and if you want to go straight, you have to tell me you want to have to go straight. If you want to go to these points, then it is straight.
Okay, then it's straight. Okay, all right, straight.
Okay.
Okay. Okay.
So from your perspective, you have to think you're
Okay.
on this position and looking in this direction.
Okay.
Yeah.
Okay.
All right.
Okay.
On this.
So I assume we both wanted to go straight.
Yeah. Okay. Now it's clear.
Okay. Now the game is clear. So I have to race here, and I want to change the color. I need a different color, so I would just take black. Well, now from the perspective of player 1, player 1 is looking to the east, predicts 2 steps, plan 1 step, there is no problem. So little as, or act as little as possible. So the next step is to be here. And for player 1, for player 2, also the same. So now play again. So first plan your actions. So player 2 said, okay, Paul, what you have to decide. You said left, straight.
Yes, I first want to have to go left and then straight. Can't I predict 2 steps?
Yes, but you have to plan just one. Take again a look at this slide. Plan your action for 1 step. So for simplicity, we have chosen here to predict 2 steps and to plan 1 step. So I assist you. So
Sorry.
player 1 is on this position and is allowed to predict 2 steps. So 1, 2. Maybe I need the laser pointer, yes. So 1 step, 2nd step. So for player 2, it is the same. You have to predict 1 step, 2. And now you see a collision at point 3. Both of you have now to act to not to collide with each other. So take a look at this slide. Don't collide with each other. So the basic task is the pedestrian walking as MPC. Follow the line, act as little as possible, consider physical and logical limits, use discrete model to anticipate your free movement for 2 steps, important. Consider your physical body limits, consider physical and logical limits on your action, position, orientation. Don't collide with each other, plan your action for 1 step. So now, yeah. Player 1 should just speak to the microphone. Player 1. What
Okay.
do you think?
Okay, then I think I want to go to the left, just to the left.
Okay, why?
Because I think that we will collide in the middle, and I just roll the dice.
But you can't see them yet, right?
Okay, I have told you. Now
I can't see it.
To say what I have written in my message, I have told you you are allowed just to avoid to the right. So this is a constraint what I messaged.
Oh,
you.
I can't. Yeah, okay. You're right. I'm sorry. Yeah, then I go to the right.
Well, now I'll put you on the right. From your perspective, and player 2.
Yeah, as I said, I will just go straight.
It is not possible because you would collide at this point, and you have already communicated both that you are going to go straight in the last step, and you both know that if you go straight, you will collide. And player 2, you did, by planning, you didn't know that player 1 is going to the right.
Yeah, okay. In that case, okay. I'll go to the left in that case. Oh, no, yeah.
Okay. Yeah. Okay. According to your constraint, you go to that.
Yeah.
So why it is deleted? Here. Okay. I hope the game is now clear. So now plan, create, and act. So you have to fix your plans before telling me your results. That's why I asked you to put it in the chat. But it is all right. You can just tell me on the microphone.
Can we?
But fix your plan.
And we can't change our plan in the game?
No, you have already decided. Yeah, now at time T, you are at this position, and player 2 is on this position, and now you have to decide again what to do. And think again, you are the MPC, which is network. You communicate to not collide with each other. So what would you do, player 1?
Okay, so I have to communicate a plan now.
Yes.
Okay, then I would communicate to
You have
I
already-
have to get
Yeah.
I have to go straight because I can't go to the left.
So you,
In that
I-
case, if you go straight, I would avoid the collision by going left.
so I'll tell you again. You have to fix your plans before telling me your plans. So player, so think that what I am telling you now about player 1 and player 2 is happening in parallel, not sequentially in parallel. So player 1 thinks now, okay, if I continue straight, yeah, I would collide again at this point with player 2. So, and my task is to follow the straight line. So follow the line is your main task. At the same time, you have to avoid collisions. Well, now you think, okay, player 2 is going to avoid the collision. You would go back to the straight line.
Okay, so the constraint with avoidance only possible to left or right, that was only when we know there's a collision and we want to avoid that collision. But if there's, like, we can still change our direction to the left or the right anyway, or can't we?
Yeah, but it just makes sense if there is a collision.
Yeah, okay, all right. Because I thought I can only go to the left. Okay, all right.
So now, from the perspective of player 2, you see player 1 is going to avoid the collision from this time step. So you don't know this plan, right?
Yeah.
This new plan. So you decide also to go back to the reference, and here we will have a collision. So we see you planned, you communicated your plans, but you collided with each other. So we will, because I know that the game is confusing, we will play the game again on the next slide. But at this time, so what happened on this slide? I wanted just to have all possible combinations, and I told player 1 avoidance is only possible to the right, and I told player 2 avoidance is only possible to the left. So I forced the 2 players to avoid to the same direction, from their perspectives to different directions, but geometrically to the same direction. So player 1 to the right, player 2 to the left, each from his or her perspective, but they avoid to the same direction. And I showed you that the collision isn't avoided. Now we will repeat the game, and yeah, actually virtually here the game is a little bit harder to play than in the classroom. But here I will tell you what I would tell you in the private chat to simplify the game. So I would tell player 1 to avoid only to the right, and also I would tell player 2 to avoid only to the right. And here what is happening is the same as in traffic. In at least if you're driving in Germany, you have to drive on the right. And if you if you're heading to each other, simply each one goes to the right and no collision happens. But I show you that a collision will happen. So again, the MPC, we start at 0, each player. Now player 1 will plan 2 steps, and or let's say again, player 1 will predict 2 steps and plan 1 step and apply, of course, 1 step. So, and player 1 is by law here allowed to avoid to the right and player 2 to the right. So as in regulations of traffic in Germany. Well, now player 2 or player 1, what would you do? Just tell me the on the microphone. We don't have to use the private chat. It is a little bit confusing, I think, in the chat.
Yeah. So right now we don't see any collision, right? It's the beginning again.
Yeah, that means you would go to straight to 1 and player 1.
Yeah, I do the same. I plan 2 steps straight and go 1 straight. Yeah.
Okay. Now both of you have communicated the plans implicitly. So player 1 said, okay, I would plan to go straight, but actually player 1 planned also in the prediction to go straight, and player 2 also planned in the prediction to go straight. So now you have communicated, and now you have to predict again and plan again. What would you do, player 1?
Okay, if I understood correctly, now I would see collision because I predict both cars to go straight. So I would try to avoid this collision by going to the right.
Nice. And player 2?
Yeah.
Player 2, you didn't know this action.
I thought that we communicated it so that I see the collision now too, like before.
Yeah, you communicated at time step 1.
Yeah.
So this step you didn't know.
Yeah. Oh, okay. Yeah, I know, but I still know that he wants to go straight. So
Yeah.
I will also have to avoid the collision.
Yeah.
And yeah, with the constraint that I have before, I have to go to the left again. Or did we change that? No, I still have to go to the left. Yeah. Or did we say the new constraint that we can go to the right? I didn't get that.
The new constraint is you are
so
allowed just to go to the right, like in the regulations.
Yeah, I will go to the right then.
Yeah. So now again, predict, plan, yeah, the communication is no matter again.
Okay, then I predict that both cars go straight, and I think there's no collision, so I just drive straight.
No, you want to go back to the line, right? The middle line.
Yeah.
So we will both.
Oh, we want to go. Okay, yeah, you're right. Yeah, then I want to go to the middle line. You're right.
Yeah, and we will have a collision again. Yay.
Yeah. So I showed you now that the strategies to go to the same direction or to go to different directions don't lead to avoid the collision. Now we play the game again, and I would tell you avoidance possible to the right or to the left. You are now free what you choose. So you can go to the right or to the left, whatever you like. So the first step is clear. You would stay on the straight. So player 1, what do you want to do?
I do the same as normal. So I go straight.
No, you
Yeah, we already did it. It's
Oh, you already. Oh, we already. I'm sorry. Oh, okay. I'm sorry. Yeah, then I would. I go to the right.
So you're free to decide to go to the right or to the left, but you have.
Yeah, but I decided to go to the right. Yeah.
Yeah. So player 2, you didn't know this action.
Yeah.
So you have decided to go to.
I don't see the difference, so I will take right again. But
Yeah.
I don't know. It doesn't help me really.
Yeah. It is the same, and you would collide again here, and we have again a collision.
We
and
cannot
I showed you there is
but
no
then
way to avoid the
yeah.
collision.
Yeah, there's no way. No. The only way is like we go back to the straight line later at a later point of time, but yeah, we're not supposed to do that.
Yeah. So this example, of course, in this example, I assumed a lot of things. I assumed perfect symmetry here between player 1 and player 2, the same step length. I assumed that if you go to the right or to the left, you land also on the perpendicular to the straight line, and that your reference trajectory is the straight line, and so on. With these assumptions, there is no way in this setting to avoid the collision. So we will see in the next lecture, I think, or in the lecture after, I don't know exactly. I think in the next lecture we will see why this is happening and how we can avoid the collision. So in this example or this game, you already know from the city center. Not during COVID, but think of normal city center on a sunny Saturday in summer. So maybe you think of the Shibuya crossing in Tokyo. If you have been there, it is an attraction in Tokyo if you go there. So the tourists go to Shibuya and observe the crossing. So it is the most famous crossing in the world. So the simple example is what we did and what you already experienced or already observed. Two pedestrians approach each other, avoid each other once, no matter to which direction, to the same direction from the perspectives of each of them, or to different directions from the perspectives of each of them. It's no matter. Avoid each other once, avoid each other twice, and if we assume the perfect symmetry and the perfect case in the game, you will collide with each other, but this doesn't happen every day on the streets. You can think why it doesn't happen every day. And if we were in the classroom, I would take a third player to the setting, and we will see what will happen. But we skip this part here in the digital lecture. But you can think of n pedestrians. What would happen if we have n pedestrians, not just two? We have n pedestrians. How they predict, how they plan, how they act, and how they really get from A to B without colliding with each other. So if you Google for this phenomena, what I have shown you, you will see many explanations and descriptions and people discussing about this phenomena. And yeah, some people say that that some wars happened because of this phenomena. So you will see in the next games more about this phenomena and about what the network brings with it. So we will just go ahead and play the second game. Now everybody is asked of you, so everybody should play, else the game doesn't make any sense. So now the game is to every one of you. If you don't understand the game, please tell me before we start the game. So the game is very simple. Choose a number between 0 and 100, and the winner will be the closest to the half of the average. So I'm telling you the game again. So every one of you has to choose a number between 0 and 100. And the winner is the closest to the half of the average. So think about it. Write your number in the chat, but don't send it. Wait until I get a confirmation that everybody has written a number, and then send your number, and I will put the numbers in an Excel sheet. So I have to. So today is a little bit confusing. I have to, at least for me, I have to change my screen. Yeah, a couple of time. So I'll share with you two. So now I have to use the other screen to see the chat. So now, please, the game is, I hope, clear to you. You have to choose a number between 0 and 100, and the winner will be the closest to the half of the average. So please put your number in the chat and click on send. Well, I have to take the numbers. Or maybe Patrick, you can tell me, then it is faster than if I look at two screens. So I have to get my laptop closer to me. So now, yeah.
Yeah, 54. Oh, sorry, it's a 4, just 4. I read you. Okay, 1, 33, 30, 50, 30, 27, 21, 56, 12, 25, 13, 72, 75, 17, 20.
Well, I have, let's see, 2. So 17 players. So some of you didn't play. So if you want to play, it is now too late. So I will look at the numbers. player number 13, I think, is the closest, right, Patrick?
Yeah, I think so. Alex
Okay,
pointed out that you wrote 27 apparently instead of 72.
He is 72.
Yes.
So now a different player is the winner, is number 15, right?
I think it's 18, no?
18, yeah, could be. Yeah, okay, let's say 18. Okay, number 18. Yeah, who said 17?
I did.
Yeah, and why?
Like I just guess, like if everyone like picks a number between like 20 to 30 or something, or like between 40, and then like we take the average and then like we divide it by 2, so it should be around like 10 to 20. So I just choose this number.
Yeah.
Just a guess.
Okay, it's good. So now we will play the game a second time. So now the same game again. Choose a number between 0 and 100, and the winner will be the closest to the half of the average. So you have now a minute to think about it, to type your number in the chat, and I will tell you if you are ready to send. So please wait. So please don't use the private chat. Please make sure that you are sending to all, so there is no problem in saying the numbers of your mates. So if you have put the number in the chat, please click on send. So again, Patrick, I would be happy if you would.
Okay, 25.
25.
9, 10,
9, 10,
16, 2, 9, 30, 7, 3, 4, 6, 10, 9, 13, 14, 34, 12,
34,
10,
12, 10,
10, 10, and 12.
and 12. So we have more players. I'm happy about the additional players, and the winner is the closest to 6 is 7, right?
That's player 13.
No, okay,
6.
yeah, 13 is the closest. So number 13, would you like to tell us why you chose 6?
Well, I think that might be me.
Okay, Sven.
Well, the idea was quite simple. We have to guess something that's half of what the average is. And so normally you would say if everybody guesses around 0 to 100, you get 50. So the half of that would be 25. And if you predict that everybody says it's 25, you can also say, okay, then it's gonna be 13. And it's going to be all the time lower. So I just guessed, well, everybody thinks no, it will be a little bit, well, smaller. So it will be 13. So because that was a guess of the last time, so I predicted that it should be half of that, and well, 6 or 7. So round up or down, and yeah. So normally we should have all guessed 0, because that would have been half, 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 and we would all win. But well, some don't predict more steps, and some, well, it shows random numbers like 30, because 30 is, well, kind of random if you try to predict. But yeah, that was the idea why I picked 6.
Very nice. And you have also already explained why you choose in the last round 12.
Yeah.
I hope you were the one with the 12.
Actually, it was 13 the last time.
13 the last time. Okay.
Yeah.
Okay, it's also fine. So, and you have already explained the whole game and the whole idea behind the game. So it is, yeah, very good. I can't explain it better. And you have also, yeah, made the last round, yeah, unnecessary, because you have said it's going to converge to 0 if we continue playing the game. And you actually the winner of round 1 was 17, but if we would have more participants, then you would with 12. So actually it is 12.5 usually the winner. So if we have enough participants, then the winner will be the 12.5 at the first round if you don't know the game. And the second round, yeah, the half of it, and so on till we converge to 0. So 0 here, yeah, is called an equilibrium in game theory, and it's called Nash Equilibrium. This is the the term in game theory. Nash is the scientist who defined this equilibrium. So I will tell you more about him in a second. I will go again to the slides. I will stay on this screen. I hope I don't have to change the screen again. So okay. Maybe this way. No. I have to change the screen where you see the presentation. So I hope I have it now. Yeah. So you have already explained, Sven, the decision quality of individuals affected by decisions of others. So you affected the decisions of each other. Yeah, this game is called the beauty contest. Actually, it was a game played in the US in newspapers. Not anymore, but in the past, and the game was choose a character, and the character will win, which is chosen by the majority. And at this point, you know, you like a certain character at most, but the character you like is not the criteria. The criteria is which character will win. So you have to think what other think. And if you continue thinking, as Sven explained, you have to think what others think, what they think about the other. So you have to think, if we have 2 players, it is more simple. You have to think what I think. Yeah. Or I have to think what you think, and what I think, what you think, what I think, what you think, this reflection levels. So if you have chosen a number close to 12.5, we say it is level 3 thinking, and in the second round it should be close to 6.25. And yeah, I would like to show you. Actually, you can read. Okay, this is the German one. I have to move this around. Okay. Now we have the English version. It's called Beauty Contest Game, and what I would like to cite what the inventor of this game, Keynes, what he said: we have reached the third degree where we devote our intelligences to anticipating what average opinion expects the average opinion to be, and there are some, I believe, who practice the fourth, fifth, and higher degrees of thinking. So this is the game I wanted to show you. And of course, if you are interested in the stock market, you can map it to the stock market and think the stock is most valuable for you is not the stock going to increase in value in the future. The stock is going to increase where the other people is thinking is going maybe to increase, and you have to think what other people think, what the other people think about the average, and so on, and you can go to more and more detailed modeling. But I think that this is enough for us today. And the next game, or in the next, okay, I have to change here to the next slide. So the next game is important for your future. So it has a sense of ecology. So we call it the Fisher problem. So in this setting, at the beginning of the game, so we have the time 0. We have a sea with 100 tons of fishes. Yeah. And N is the number of the players. In our case, it's going to be the number of the groups. So we are going to play this game in groups. So A, B, C, D, E, and I in this modeling is the player. So group A is 1 and E is 5. So, and your action is going to be limited between 0 and 10, and it is the weight of fishes you fish from the sea. So you can fish something between 0 and 10 tons. And yeah, here is the model. So the number of fishes in the next round is going to be 1.2 of the number of fishes in this round. So this says that the number of fishes increases by 20%. And it's minus the number of or the weight of fishes you have fished. The sum of fishes fished by all groups. Well, and your task is going to be to maximize the weight of fishes you fish over time. Yeah. So you have to, for your group, to maximize the weight of fishes you fish, and you are allowed to fish in each round between 0 and 10 tons. And the constraint is we want to have at least 1 ton in the sea to have fishes in each round and to continue having fishes. So we don't want the fishes to die completely. So do you have questions about this game? So if there are no questions, I would like you now to go to the breakout sessions. You will have 2 to 3 minutes to discuss about, in each group, to discuss about the weight you want to fish from the sea. And you will come back and please fix a number. So fix a number and come back, and you will have to tell me the number. So please go to your breakout sessions. Okay, then we continue. So I hope every group has decided. So we are playing here groups against each other, and you have to win. So you have to maximize your fishing. So I need 1 person from group A to say a number.
10.
Okay.
Sorry.
So I hope you have fixed your numbers. So B.
10.
Also 10. C.
3.
D.
2.5.
You said 5.
2.5.
2.5. 2.5.
Okay, we have 2.
2. Okay. Now we have still 92.5. So we play again the same people. You said the numbers now for the groups. So we are going not to discuss again in the groups. So each one of you, please take just some seconds to think about a number and tell me the number, and I will type the number. But please be honest and fix your number. So group A.
Well, we're sticking with 10.
B.
I think we're also sticking with 10.
C.
2.
D.
Same as last one.
Same.
Yeah.
E.
2.
Say it again.
2.
2.
Same. Yeah, same like last one.
Okay, same like last one. Okay, till now, group A and B are the winners. So we will continue the game. Please think now. You have some seconds to think, but please be honest and fix the number. So I would say now, so I would start now with other group. So group E.
We stay at 2.
2. D.
Also the same.
Also the same. C.
2.5.
2.5. B.
10.
10 again, and A?
10.
10. So question to group A, if we continue the game, would you change your mind at some point?
No.
No, you wouldn't change your mind. So group B, would you change your mind?
No.
No, you would continue. So group C, you had 2, 2, 2.5. So would you change your mind radically?
No.
Okay. Group D,
Stays the same.
you don't want to change your mind. And E,
I think it doesn't matter if we change our mind now.
okay. Then we see at round 9, we don't have fishes anymore. So the last round we had fishes is round 8. And we see that the winners are group A and B. And actually, they are the winners of this game, and they are equal. So there is no difference between groups A and B. And maybe one of you, maybe group A, why have you decided to stick to 10?
We thought that there's like 2 options. We either go fully greedy, so the maximum, if we assume that someone else is gonna be greedy, or everyone would choose 4 if it's the optimal point. But well, we obviously thought that someone else would be greedy, so we also decided to be greedy to maximize our winnings.
Okay, so you played the right game to win, but just against the others, but you didn't think of your future. So you should know that you now in round 8, not just you, but all other groups don't have anything to eat. No food there. No food more. Or no more food. So it is the same here. And one of groups C, D, and E, let's say group D, I would say group D, the player of group D, why have you decided for 2.5 and to stick to 2.5?
So the general idea was that if there are no more fish, everybody loses. So just stick something where at an average, which we calculated that the population of the fish doesn't change if 16 tons per year are fished, and then take a little bit less in the case someone takes more. So instead of 3 point something, just take 2.5. But if people are greedy, everybody loses. So I think there's no winner here, only losers.
Yeah. So it is actually easy in this game to know if we are greedy, we are going to lose all together at some point of time. And if we are cooperative, and we will speak in this part of the course more about the word cooperative, and we will define it mathematically. So if you were cooperative, you would continue fishing, and you would continue winning from round to round, infinite. So in this game, group A and B were the winners, but they contributed to the loss of all groups, because you cannot continue playing now anymore. The sea is empty. So now with this game, I wanted also to raise your awareness about the ecology and about how we should think in the next years as human beings, and how we can contribute to our end, or to our at least to continue. You see in this game, we have to have a certain number of people cooperating. I am not saying that all have to cooperate, but the majority have to cooperate. Yeah, and if you cooperate, we can exist. If you don't cooperate, we end. So this is the message. Actually, the message is also for the course. It is not just for the ecology, but it's also yeah, right from this point of view. So I'm not going to have the discussion more in this lecture, but think about the Fisher problem as MPC. So, and discuss the effect of the prediction horizon. So if the prediction horizon is a certain number, what would happen? Just think about it for yourself, and maybe with your groups, you can go to your wonder sessions. So on the next discussion point is the MPC algorithm is greedy if the prediction horizon is, so you have to answer this question. So how long is the prediction horizon to lose or to win or to be greedy also? So computer scientists like to divide algorithms in greedy and non-greedy algorithms. And if we think of MPC as an algorithm, then the MPC algorithm is greedy if the prediction horizon is okay, a discussion point. So the next game is this lecture. So we have at the beginning, so before we started the lecture, 0 participants. The number of participants in total is 30. I is your index, and you have the choice. You participate or don't participate in each lecture. So the number of participants in the next lecture is the sum of use. If you participate, then 1 plus 1 plus 1. If you don't participate, 0 plus 0 plus 0. So we have at the end the number of participants. And it is weird for me to say it, but this is really the task, to minimize the number of times you participate. Maybe you decide to listen to the lecture in Moodle, and you are more flexible. So you have to minimize the number of your participation in the lecture, but you should know that in each lecture we need at least 18, else I wouldn't upload the recordings to Moodle. So you know, if for you, or you already know, if you participate, you have already participated. If you don't participate, you have to trust at least 18 people to attend, and we need at least 18 attendees to record the lecture and to upload it to Moodle. So I thank you for your cooperation. So in each lecture we had at least 18, and we uploaded each lecture till now. So please continue cooperating for the next lectures. So there's also a discussion. So it is also for you, it is homework. So this lecture as MPC, how long is the prediction horizon, and what is the best strategy? This is controversy discussing this discussion point. So what is your best strategy? So do you want to attend each lecture? Which lectures can you miss? if you miss, maybe you have totally missed. So you have to discuss about your best strategy. And the next and last example is the COVID-19 pandemic. And I'm going to have a weird modeling of it just for simplicity in this lecture, okay? So before the pandemic, we had 0 infected people. And let us model Germany. In Germany, I assumed we have 80 million people, the number of population, and we index them, and they are either infected or not infected. So there is no way to, it is a binary decision. Or it is not a decision, but I'm modeling it as a decision. This is the weird thing. So each one is either infected or not infected. So the number of infections in the next day is the number of infections today plus the new infections, and R is the famous R you know from the news. So the number of the rate of infection, and minus are out the rate of outgoings. So they may be getting healthy, or they may leave the system, maybe unfortunately die, or leave the system of Germany, because we are modeling here just Germany. And in XT is the sum of infections. So our task for economy, so that's what I said, it is weird modeling, but it is actually the model the politicians decided for. So we have to maximize the number of infections, as you see here. So this is the sum of infections, and we want to maximize it, but we want to have a rate of infections. So the intensive patient, the rate of patients need a bed in the intensive station of the hospital should be, so the rate times the number of infected should be less than a number. I chose here 30,000, maybe it's not the exact number. So this is the number we have in Germany. So what we want to do with this example, or with this game, we are interested in maximizing the number of infections, but we don't want to overload our health system. So this is again a different game of network systems, and I hope today with different games I could raise your awareness about network systems and about the importance of the network and what the network brings with it. So it is not just the single agents together, there are effects happening. So with this, I would like to close today's lecture, and the next lecture next week is going to be a flipped classroom. So we are going to upload the slide of preparing the next lecture. So see you next week. Bye-bye.